the standard cell library?
Okay, so if we delve a little bit into the details, it's not precisely that there's a supply voltage difference, but one of the reasons why you might say, okay, why is this DSP block not as good as the Stratix DSP block? You know, that seems like a fairly easy thing to get on par. And the reason is that we just think that the standard cell library that we're using and the technology is just not as highly optimized. It's very likely that they're pulling up all of the stops on TSMC's 40 nanometer node to get high performance transistors, lots of leakage, to get these things as fast as possible, and we're not doing that. We're just using a standard library. So that's probably why we're getting so much less performance. So that's something we have to analyze in the future.
But do they have the same supply voltage? I can't remember.
There's no way to tell. They might not. They might be boosted. It's possible, but I don't know.
The DSP blocks aren't boosted.
Yeah.
So it would be whatever the nominal voltage of the process is.
So we suspect it's a transistor difference. They're using basically high leakage transistors that are fast. That's the only thing we can come up with, because we can't beat their numbers even if I don't have any fracturability. Even if I just synthesize a multiplier, it's not as fast. So it's a technology difference basically there. But yeah, not to go into too much detail. Okay, so on area, we're about sort of 2x away from a Stratix. And what you can see from this breakdown here, when I say core and total, is that total includes the routing area. So what you can kind of tell is that the routing area is usually double the size of the block itself. And that's sort of relevant. We really need to optimize this routing if we're going to get closer, because having sort of so much routing area in common with all of the blocks is sort of holding us back. So that's really sort of the takeaway from this.
So just to clarify here, the core synthesizable area for a lab is just the lab itself with no surrounding routing. So it doesn't have even the intra-lab routing, or it does have the intra-lab routing?
So it does. So basically what this includes is, these two figures include, is both the block itself and all of the configuration inside of it, but also the corresponding switch block and connection block and all of the other routing stuff that's needed at that particular tile location. We'd like to break it down better, but this is still sort of what's available in terms of figures. They don't really have a detailed breakdown publicly available, so this is sort of where we're at in comparing them. But what we can see from this basically is that we're probably losing some area here, but we're definitely losing some area in terms of routing and interconnect.
Is this post-synthesis or post-place and route?
This is post-place and route.
So did you choose like the same packing density, like the same core ratio to like place and route for the DSP or and the lab, or did you choose different ones?
So everything was done at not approximately 80% density. And that was basically done because if we could get more density, of course, but the performance, you lose performance.
So did you target for the DSP and lab to have exactly the same area, or like did it just happen?
So it basically just happened. They ended up being really similar. Yeah.
So right in your floor plan, the RAM tiles are height 2. They're 2 lab tiles high. Is that correct?
Yes, that's correct. And that's
the
why there's
SP tiles are sort of pitch matched with the lab tiles.
Exactly. Yeah. Okay. So so basically, what we can see from those results is that we're about 2x away on area and performance. Oh, sorry.
Yeah, sorry, I just had a question about the last slide.
Oh, no problem.
Kind of, what is the core area? Does that include kind of like the input-output mixing, or is it basically like for the lab, it's just the LUTs and blocks? And then the second question is, what would you expect as a ratio of kind of like routing area to logic area? Because to me, this seems like 1-to-1. I would almost expect more routing area than this.
So we would expect, well, one is that we sort of have oracle knowledge that the routing isn't as good as we'd like, because we've done experiments in another tech node where we did some replacements of the standard cells with more custom logic, and we found a big decrease. So we obviously already know that we can make it smaller. And that's not sort of not including very detailed floor planning and things that approximate custom design. So we do know that we can make it smaller, and just sort of having looked at sort of the ratio between sort of full custom multiplexers and standard cell multiplexers and the density we're aiming at, I know we can get this this smaller. So I guess I am sort of inferring that from other information, but it's definitely true that the routing is costing us on every single block. No matter what block you add, the routing is still going to take up a lot of area. So it's sort of a common element. It's half the area. We need to make it smaller to get better performance. That makes sense. And as far, I can't remember your first question now.
I was wondering what's included in the core.
Okay, so that includes, for a lab, for example, that includes all of the sort of local interconnect between different LUTs, but it doesn't include the sort of the connection block stuff. So it's basically, and if you look at a DSP, it's everything everything that isn't routing. So if that makes sense. So not the switch block, not the connection block, but absolutely everything else, including configuration. Yeah. Okay. So I'll just finish up really quickly. So the future work here is that the number one thing is that optimizing this routing network for performance and area is really important if we want to make this more competitive. Another thing too is that for configuration, I did mention this earlier, but we're using flip-flops, whereas an FPGA would use SRAM cells. So that's important to optimize if we want to get better density. But some other things as well are that we don't actually have accurate timing and power estimation of this yet. We're sort of just doing very crude backporting of timing back into DPR to get it to map, but it's not really detailed. So we'd like that to be better. And the other thing is we'd like to exercise these domain-specific capabilities, add in some new blocks, do a case study to see if these sort of domain-specific FPGAs domain-specific soft FPGAs can be used for applications with some gain. Yeah, and that's it. Thank you very much.
Okay, so we'll move, since we have another talk, if you have questions, maybe you can ask after later. So the next talk will be by Ibrahim Ahmed, and he's a PhD student of Von Metz.
Hi everyone, thank you both for the introduction. Today I'm talking about our paper that was presented in this year's FPL entitled Automatic BRAM Testing for Robust Dynamic Voltage Scaling for FPGAs. So let me start by showing you this graph of these two curves showing CPU clock and power across different technology nodes. And so in earlier technology nodes, CPU design was mainly clock frequency driven. With every new CPU, we wanted to have a higher clock frequency, and that was the main driving factor. Until we hit the power wall, and then we started designing power-aware CPUs, right? We started focusing on decreasing the clock frequency and using multiple cores instead, and looking into adaptive power management techniques such as dynamic voltage scaling. But why am I showing you this curve? FPGAs have great power consumption, right? Well, unfortunately, not anymore. So if you compare the two black curves, which is the FPGA power consumption and the CPU power consumption, you can see that with in earlier technology nodes, FPGAs did have a great power consumption compared to CPUs. But recently, especially with the latest Stratix 10, power consumption made this huge leap, and now FPGAs are almost in the same ballpark as CPU power consumption, if not more. So this was the motivation for our work. We believe that FPGAs need power management techniques too, just like CPUs did a while back. So to get some rough estimates on how much power would we be saving using a dynamic voltage scaling technique on FPGAs, we ran this experiment where we got a FIR filter. It's a feed-forward application. We compiled it through Quartus, and Quartus said that, so this design running on a cyclone 4 with a fixed nominal voltage of 1.2 can run at 110 megahertz. So we had a cyclone 4 chip, and we actually measured that, and that's what you see here in the blue line. So the blue line here is the measured Fmax at different supply voltages. And what you can see here is that because of having pessimistic timing models that are necessary for safe operation across different chips and applications, you got this gap, right? So this gap is necessary to guarantee safe operation. but it also creates a gap between what our silicon can provide and what we're actually getting from this silicon. So if we look at a traditional FPGA market where an FPGA would run a static application using a fixed frequency with almost no timing margin, a dynamic voltage scaling mechanism that knows that, yeah, for this specific speed, we can actually run this chip at this supply voltage instead of 1.2, we'll be saving more than 30% total power. And more interestingly, if you look at the new data center accelerator market, in which an FPGA would run different applications with different timing margins, different workloads, and it also has the capability of running at variable frequency. Dynamic voltage scaling would enable FPGAs to have CPU-like power management, where we can decide a trade-off between power and performance, and we can get up to 50% total power reduction. Okay, so now that we know the gains that we could get from DVS, let's see what are the challenges. So one of the main challenges of any DVS solution is how do you find what's the minimum safe voltage for each frequency? For FPGAs, this is specifically more challenging because at the design and manufacturing time of an FPGA, you don't really know what's the critical path, unlike CPUs where you exactly know what your critical paths are. So there has been some academic solutions on how do you answer this question. One of the interesting solutions was using an online monitoring, where you would add a shadow register for each timing critical register, and you would use that register, these shadow register, to determine what's the minimum safe voltage. Another approach that we have proposed earlier is an offline calibration, where we would extract the timing critical paths of an application, perform an offline calibration to determine what's the minimum supply voltage at different clock frequencies. One major limitation in these two approaches is that they both assume that the timing critical paths that should be monitored or calibrated are only using the soft fabric of the FPGAs. So we started this work by running an experiment to check whether this is true or not. So our goal of this experiment was to analyze many different critical paths across a suite of benchmarks shown in this table. And we've discovered that almost on average, 60% of these critical paths are somehow connected to the VRAMs, either feeding a VRAM or inside a VRAM or being fed from a VRAM. And this drove this work where we extend our previously proposed offline calibration to provide the first solution to handle DVS on an FPGAs that use VRAMs. Now, this is the outline of today's talk. I'm going to start by briefly giving a background over the offline calibration approach that we proposed and how could VRAM fail as you scale the supply voltage. And then I'm going to say how we extend this approach to test for these types of failures. And finally, I'll show some power savings numbers using our proposed DVS solution. Okay, so let's see how this calibration approach works. So in a normal design cycle, a user would write an application, HDL or in some C language, in some high-level language, and then a user would feed this application to a CAD system, for example, Quartus, which would compile this application and gives the user an application bit stream. What we propose is slightly adjusting this flow. So from a user perspective, it's still the exact same thing. The user would write an application, feed it to the CAD system, but we've made the CAD system slightly more complicated by adding FROC. This is our CAD tool. And what this FROC tool does is that it analyzes the application of the user, and then it generates this calibration bit stream using Quartus. This calibration bit stream includes replicas of the critical path of this application, heaters, and some test circuitry. And the idea behind this is we're going to use this calibration bit stream to measure what's the minimum safe voltage for different frequencies and different temperatures for each application and chip. And the output of this calibration phase would be these calibration tables that say, okay, for this chip running this application at temperature T1, you'll have this table that says, yeah, if the user wants to run at a certain frequency, then this would be the minimum supply voltage that is able to support this frequency. And finally, we'd have now this calibration table stored on the FPGA, and while the application is running, we have a small module that monitors the temperature, looks up this lookup table, and then determines what's the minimum supply voltage. So this is how the flow works. And we've shown that it works well. We're able to reduce power consumption on a couple of benchmarks, but it has this limitation that it can only handle soft logic. So in our previous paper, we had to selectively pick applications that don't use BRAMs, which is a big limitation. Okay, so now before talking about what could go wrong with the BRAM, let's give a very quick overview of BRAMs in an FPGA, right? So you have an FPGA. Usually BRAMs are organized in these columns, and you talk to the BRAM and from the BRAM using the soft fabric. So the soft fabric would write data or read data from the BRAM. And the BRAM itself is composed of standard SRAM cells, right? You have the back-to-back inverters and the access transistors, the sense amp, and this whole SRAM cell. So what could go wrong as we scale the supply voltage? So looking at the SRAM cell itself, you can have multiple failures that are grouped under the name of parametric failures. These failures include retention failure, where you're scaling the supply voltage so much that the SRAM cell could no longer retain the same value. It would flip the cell. The other type of failure is a destructive read failure, where you're trying to read the SRAM cell, but because the supply voltage is too low, you would flip the cell, the information stored in that SRAM cell. The third type of failure is an access time failure, where your clock frequency ends up, your supply voltage cannot handle the clock frequency you're providing to the BRAM, and you'd end up not being able to read or write the SRAM cell itself. Now, the other types of failures, we group them under BRAM interface logic, right? So you have your soft fabric talks to the BRAM and gets information from the BRAM. So you could have a timing violation in the paths that feed the BRAM, or you can have a timing violation in paths that come out of the BRAM, right? These paths could start from the output port of the BRAM if the BRAM is registered. They could start from the input port of the BRAM if the BRAM is unregistered. And what we did in this work is we basically extended FROC to automatically analyze the user application and test for both of these kinds of failure. The failures inside the SRAM cell and the failure in paths that feed or come from the BRAM. And this gave us this new tool that's able to provide a DVS solution for applications that use BRAMs. Okay, now I'm going to talk about how do we actually test these two types of failures.
Ibrahim, just to clarify, you know the calibration tables that you generate that you talked about, that would be done sort of at the right after manufacturing time, right? That would not be done by the user, is that correct?
They would be done at the user side. So the user would give the application to the CAD system.
Yeah.
The CAD system would generate like the calibration bit stream, and using like the calibration bit stream is able to talk to a spot power supply that we have, and it will perform the whole calibration on the user side. And
So
it takes
and the calibration then considers the design, so it's for that particular design.
Exactly,
Gotcha.
exactly.
Yeah.
So it's an application specific
Gotcha.
scheme. Okay, so now let's see how we test
That design.
the parametric failure. So starting with the retention failure, because it's simple to explain. Remember, retention failure is when you reduce the supply voltage too much that the cell can no longer retain its value, and it just flips it without any read or write. So what we do to test this type of failure is we write a specific data word in every cell of the used BRAM. Then we would reduce the supply voltage. We would wait for some time to check for to make sure that the chip is able to retain the data stored at this supply voltage. And then we would increase the supply voltage back to a safe value, and we would perform a read. If we read the same value that we've written, then that's good. We can go back and reduce the supply voltage and repeat this step until we find the minimum voltage that can maintain the value stored in the SRAM cell. For a destructive read failure, it's almost the exact same procedure, but instead of waiting at the low supply voltage, we actually perform a read to stress the SRAM cell. For the read access failure, I won't go into the details, but the main difference between an access failure and a destructive read and retention failure is that access failure, we need to find a pair of information, voltage and frequency. Because for each frequency, you have a different minimum voltage. So we perform this type of test, and an even more complicated test is the right access failure. So I'm not going to go into the details of these two types of failure. Okay, so now that we know how are we planning to test these types of failure, let's look at the challenges from the hardware side. So we want to test the speed of BRAMs, which are a hard IP on the FPGA, using the slower soft fabric. So this is a big challenge. And on top of that, we also want to test all the BRAMs at the same time. So we want to have almost a fully populated FPGA and at the same time we want it to be running faster than the DRAM itself, which adds even more challenge, right? And because we're testing at different supply voltages, not only the nominal voltage, we need to make sure that our tester is able to run faster than the VRAM at these different supply voltages. So we set our goal to be the following. So Quartus reported that the speed of the VRAM is 314 megahertz. So our target now was that we need our tester to run at 500 megahertz, which would give us enough margin to be certain that any failure that we read is coming from the VRAM and not our tester itself. Okay, so to achieve this, what we did is we designed parallel testers that would multi-pump the VRAM. So we'd use time division multiplexing and demultiplexing, and we would now have these two testers that test a single VRAM. Using such a scheme, we're able to clock these two testers with 250 megahertz while maintaining the speed of 500 megahertz requirement that we have. The only problem is that our time division multiplexing and demultiplexing still need to run at the 500 megahertz. So we look at a single VRAM where we instantiated one tester to test a single VRAM, and we checked that our Fmax actually met our target, right? So we were able to run this tester at almost 600 megahertz, which was good. So we moved in and said, okay, now we want to test all the VRAMs in parallel. Once we did that, the frequency dropped all the way more than 50% down. We noticed that Quartus was trying to optimize to share some logic between the testers, but because we know that they're independent, so we partitioned them such that Quartus doesn't do this optimization, and we actually got some frequency and logic utilization increase, but still nowhere near what we want. We went one step further and we floor planned our design manually. We know exactly what we want. So we got another frequency bump, but again, it wasn't anywhere close to what we want. But we noticed something interesting, that some of the testers actually meet timing. So some of them don't, but a chunk of them actually need timing. And because we know that they're almost identical testers, we know that there is no fundamental reason why the others can't meet timing. So we developed this iterative compilation where we fix all the netlist, and then we just look at the slowest n testers. We free these slowest n testers and run a compilation again. So in this compilation, Quartus is only compiling a subset of these testers. And interestingly, with every compilation that we do, we notice that some more testers are meeting timing. And after a couple of iterations, we're able to meet timing for all our testers. And we've managed to get almost 90% of the Fmax for a single tester. And we did that for our testers, but we think that this is applicable for any other regular design. Okay, so now going into some results. So we tested seven different cyclone chips for all the parametric failures. We couldn't find any, across the operable voltage range of the chip, we didn't find any retention or read destruct failures. Looking at the read and write speed, this graph shows the average, the min, and the max of the write and read speed across all different VRAMs in the 7 chips across different supply voltages. So a couple of interesting things to note here is that the average VRAM runs 60% faster than what is reported, and the variation between the VRAMs could go up to 20%. Now, looking at the spatial variation, so here because our tester is able to determine the Fmax of each VRAM, we're able to draw this heat map, which shows a cycle 4 FPGAs, and these are the VRAM columns, and you can see the Fmax of each VRAM column. So one interesting thing is that in this specific chip, the lower left corner VRAMs tend to be faster than the rest of the chip. We measured each VRAM column across the different chips, and so this new column shows the second chip, and then this new extra column shows the remaining chips. And another interesting thing is that the first chip, one of the chips is consistently faster than the others. So while these are interesting, the main takeaway here is that the user shouldn't really care about this variation. With our dynamic voltage scaling scheme, we're able to measure the specific VRAM that you're using. We're able to get the maximum utilization of the silicon that the user is using. Okay, so before going into the VRAM interface logic, I just want to say now that we're now able to test the parametric failures of the SRAM cells itself. We have confidence that our dynamic voltage scaling scheme would never result in an error from the SRAM cell itself. The next thing we need to check is we need to check that we don't cause any timing violation to paths that feed or come from a BRAM. And this is challenging by itself. So comparing these paths to just a regular path that starts and ends in the soft fabric, you have the BRAM itself could have different modes, could have different depths, different widths. It could have registered or non-registered outputs. So to handle these issues, our tool analyzes the BRAM used by the user, and we replicate the exact same mode. The other major challenge is that these registers that are inside the BRAM, they're buried inside. You have no observability on the input or the output of these registers. And each register could have different functionality, right? So you could have like an address in of a write-only port, or you can have a write-enabled port. Each register has a completely different functionality and a different way to access it. So how do we handle that? FROC checks what type of port is this path using, and then it performs a multi-stage testing in which it would first, let's assume now we have a critical path that starts at the source fabric and ends at an address port of a write-only BRAM port. This is common in a FIFO, right, where you have one port that's only writing and the other port is reading. So let's say you have a critical path that ends at the write-only port. So FROC, our tool, would replicate the exact BRAM in the exact same mode. It would replicate all the critical paths that feed this port. And then it would add memory and test controllers that control the untested ports of the BRAM. It would perform a multi-stage testing where it would initialize the BRAM to a known state. So it would write some data in the different words. Then it would activate the fault by trying and writing a different data in the BRAM. And then it would propagate the fault by reading that word. And by determining whether the write was successful or not, you know whether this was a safe VDD or not. Okay, so let's take a step back and look at the scheme I showed earlier. So this is the original proposed offline calibration scheme that only worked for soft logic. By adjusting FROC to handle testing the BRAMs, we're now able to generate more powerful calibration-based schemes that test for BRAM parametric failures, interface calibration, and the logic. And this enabled us to test applications that actually use BRAMs. So I just have one last slide showing some results. So we wanted to test that this works in hardware. So we got a discrete Fourier transform benchmark. It uses BRAMs. We said, okay, let's run it with the original FROC that didn't test BRAMs at all. So we got these, we ran it on two different chips, and we got this Fmax versus voltage curve from the two different chips. And Quartus said that this can run at around 150 megahertz. Our calibration table that ignores BRAM said that, no, actually it can run at a much higher frequency, and this is the Fmax across different voltages. So it looks great, but is it safe? So to answer this question, we tested the benchmark itself for with a known. We tested the benchmark itself to see if it fails or not, and we got these two solid curves. So these two solid curves came from testing the benchmark itself on silicon. And what these two curves say is that the calibration table that we got is actually unsafe. It overestimates Fmax significantly, right? So it tells us that at 1.2, we can run all the way up to 250 megahertz, but the application would actually be failing timing at that point. Now with our new work, running the generating a calibration table that takes into account BRAMs, we're able to generate these two curves that show that, no, this is actually now safe values to run your application at. And we're able to, if you want to run this application with no timing margin, you'd get around 32% power reduction. If you have some timing margin and you want to run the application at 100 megahertz, you'll get up to 46% power reduction. And so finally my conclusion slide, so we can go to the pizza. So in this talk, I basically presented the DVS solution that handles BRAMs. To the best of our knowledge, this is the first work that handles DVS using BRAMs. And our CAD tool automatically generates all these BRAM testers, so the user doesn't have to add any manual work from his or her side. And our silicon measurements showed up to 46% total power reduction. And thank you.